Welcome to the last lesson of the course Paradigms of Computer Programming. In this last lesson, we're going to take a look at all the paradigms we saw, the three paradigms, and then we're going to situate them in the context of many more general paradigms and why they're useful and how the paradigms are organized. And then, how do you pick paradigms? Which is best, if any? So in this course, we saw three. And let me first recall the definition of a paradigm. So it's an approach to programming a computer based on a coherent set of principles or a mathematical theory. So there are a number of these: lambda calculus, pi calculus, first order logic for logic programming, Hoare logic for imperative programming, and so on. And then there's theories used in object-oriented programming of data abstraction. And in fact, no one existing theory covers all these programming concepts. In fact, programming is really a new discipline. It's not covered by any single traditional mathematical theory. It's like a constellation of many different theories. So in this course, we've covered three important programming paradigms. I'd like to recall the question, why do we need more than one? Why is not one sufficient? In fact, one is not sufficient because different problems are solved best with different techniques, and each paradigm brings in different techniques. So you can see this in the real world. For example, carpentry, which uses wood as a basic material, metalworking, which uses metal, masonry, which uses stones and bricks and cement. They're all materials. Why do we need more than one job? Why do we need more than one discipline? Well, it's easy to see when things are so different as wood and metal and stone. In programming, it's the same. There are problems that really require different materials, different concepts. And so that's why we need different paradigms. So in this course, we saw three paradigms. We saw the functional programming paradigm, the object-oriented programming paradigm, and the deterministic data flow paradigm. So the functional paradigm is based on functions, higher order programming. It uses recursion. It also has single assignment variables. This is not always done in functional programming, but it's very important. It lets you make many more functions tail recursive, but it also pays dividends when you go into later paradigms, such as concurrency. Object-oriented programming brings in a number of techniques for building large programs, for structuring them, for building them in teams, for making sure we can reason about them and their correctness. So the notions of data abstraction, polymorphism, and inheritance. Deterministic data flow brings in concurrent activities, but with very special properties, no race conditions, so the activities do not interfere with each other. We have concurrency transparency, which means we can create as many activities as we want without breaking the program, without changing the result. And the techniques we use streams and agents. Notice it's quite different, deterministic data flow, from object-oriented programming, and they're also quite different from functional programming, the mindset, the techniques that you use. But the kernel languages are very similar. There's the functional kernel language. We add cells to get object-oriented programming, and we add threads to get deterministic data flow. So with these very similar kernel languages, we get paradigms with very different mindsets and very different techniques.